Welcome to the Introduction to Scholarly Information Extraction. I'm Wolf Otto. I'm a research associate and postdoctoral student working on scholarly information extraction as a topic for my thesis. This presentation also includes contributions from my colleagues in the Department of Knowledge Technologies for the Social Sciences, Lou Gan, Saurav Kamaka, and Philip Meyer. Together, we bring decades of experience in computer science and data science, specifically in the fields of natural language processing and bibliometrics. After my introduction, I will give three demonstrative examples, a in-depth view of one scholarly project, and last but not least, scholarly information extraction in production. Most information used to discover research is basic metadata. However, the majority of existing scientific information is hidden in natural language in the body text of research publications. We identified four categories of information hidden in publications. Additional to metadata, the second category is semi-structured information. This includes references, images, captions, and other. The third category are in-text research artifacts, so mentions of dataset software methods and variables, but not in the reference section or in footnotes, but also in the fluent text. And lastly, the fourth category are in-text, in-domain information. So this could be constitutional institutions for political science research or genes and disease in biomedicine. This information is mostly about the research object itself. But what can we do? Why should we extract this information automatically? We can enable a new quality of fair research, for example, for dataset software and models, make them findable, accessible, interoperable, and reusable. We can help foster research quality by supporting the verification of reproducibility. And we can answer domain-specific research questions. So if we are able to turn scholarly documents into structured knowledge, we can enhance discoverability. So it's easier to quickly locate relevant research. We can comprehend insight gain a broader perspective of science and identify trends and gaps in the literature. We can enhance reusability and reproducibility, and we can improve comprehension, for example, with accelerated literature reviews or the easy access of key concepts and relationships between the concepts. And of course, this structured knowledge needs to be usable for the researchers. So we need interfaces and tools to let the researchers access this structured knowledge. We define information extraction as the task of extracting relevant information from text and documents. The state-of-the-art pipeline integrates named entity recognition, which is the identification and classification of named entities in text. So given a sentence from a research publication, we identified relevant information for our information need, and we classify the type of information. In this example, dataset and data type. The second step includes the relation extraction. So we link the mention of the dataset in our example to the data type and classify the relation type, for example, has instant type. The next step is entity resolution. So given many mentions of the same dataset, which might look different, in this case, Flickr data versus the YFCC 100 million Flickr data, we merge the mentions into clusters and identify these clusters identify one concrete entity in the real world. And lastly, the entity linking, which is link those unique data sets with external existing resources like databases or knowledge graphs or knowledge in web pages. Here, for example, with paper with code, we create the link and then add the information that this found data set is identical to the one which is mentioned in this on the web page. To even demonstrate this further, I show you 3 examples. The first one is on the semi-structured information type. It's a project called Outside, and the goal is to understand references and reference usage in social sciences. Here you see a pipeline which reuses the steps I shown before. A first step identifies relevant sections where references are mentioned. The second step, the extraction step, extract from the reference strings relevant information and transform it to structured knowledge. And the third step is to link to external databases, in this case, for example, OpenAlex or Crossref, to be able to get URLs for open access representations of the publications or DOIs from Crossref for the publisher full texts. The second project I want to show is SAMSci and Software KG. Here the goal is to monitor software usage in research. Given a corpus of biomedical and social science publication, the task is to extract and link software mentions of 5 different types and attributive information, for example, the developer or the URL, and additionally classify the intention of the mention. For example, disambiguate creation and usage of a specific software. Those developed methods are then applied on larger corpora, and knowledge graphs are created out of this, able to show somehow for example, the different usage in specific subdisciplines of software and the practice of software mentions in scientific publications. The third project is unknown data, which has a focus on linking data and research data sets on different sources, namely web crawls of research institutions, scientific publications, and existing databases and databases for data and publications. This project also includes the whole pipeline of entity extraction, entity resolution, and linking. The result is not only an integrated database, but also the enhancement of the data with new unseen data sets, which are hidden in research institutions or other websites, or scientific publications, but are yet not in databases or for data or publications. In the following minutes, I will demonstrate which aspects of for scholarly information extraction you need to follow in a concrete project. And for this, I use GSAP. It's the GESIS Scholarly Annotation Project, and it's focusing on entity extraction of machine learning models, datasets, and related information. The overall perspective is to improve the reproducibility and reusability of machine learning research. So one aspect is to track models and data. So answer questions like which model is trained on which data set, or what is the data source of each data set. The second aspect is documenting model architectures to be able to say which model architecture is applied on which specific task, for example. And GSAP NER is a key component to address these questions by detecting dimensions of the relevant entities. The contribution of the project is threefold. On the first we create a data model which is able to define what is relevant data in our context, and to define relevant entities and related relations. The second part is a corpus, which consists of 100 research publications from the computer science domain. And the third part is a model which is trained on this data and is able to be applied on a larger corpus. Here you see an example from the dataset from one publication of the 100. And as you see, we are not only interested in concrete mentions like the Flickr dataset mentioned before, but also in generic mentions like our dataset. With this, with the help of those generic types, we are able to capture most of the entity mentions, even if they are not named. And on the right side, you see one sample of the annotations of the follow-up of this project, which identifies the relation between the mentions. To come to a text set which is able to model our domain appropriate, we start from a conceptual data model, differentiating between resources and concepts on the other hand. So in our use case, scholarly artifacts like machine learning models, dataset, data sources, and publications. And on the other hand, scholarly concepts like methods, tasks, and for example, model architectures. And we transform this to a text set ready to be applied by our annotators to annotate the full text. As you see, as an example, publications are not mentioned directly, but indirectly using reference links. For the creation of the corpus, we choose archive as a data source because of its relevance for our research domain and because it's open accessible. Based on this, we decided for two sampling methods. On the one hand, popularity, given mentions of archive publications in README files of popular Hugging Face models, and on the other hand, to represent the long tail of the publications, variability. So we randomly select from a given category, machine learning, from archive publications of the last 5 years, and additionally filter with string matching based on model and data mentions in the abstract. And finally, we process the PDF documents using Grobit for PDF to text and Inception, load it into Inception, which is an open access annotation tool. The annotation process includes 3 annotators and 3 lead annotators. And a part of the annotations, or a part of the 100 publications, are not only annotated by one annotator alone, but by all 3 annotators. This is to make sure that the style of the annotations of the annotators and the understanding of the concepts of our annotation text set is comparable. This ended up in around 54,000 annotations and over 500 annotations per document. For the model we trained as a baseline for this task, we decided for a supervised approach. On the one hand, it's still state-of-the-art for domain-specific named entity recognition. And it is a scalable approach without the limitations of big, large language models. We use transformer language models, which are able to classify each word in a publication of the existence of an entity. And the goal of this classification task is to reproduce the annotations. We also experiment with domain-specific model pre-training, which is we start from models which are further pre-trained on research publications, and one model also namely on computer science publications. And when we fine-tune those models using the task of named entity recognition, we found out that even if it's not the biggest model, CITEBERTA CS, which is additionally pre-trained on computer science publications, outperforms the much larger Roberta large model. And we evaluated the model with metrics representing how correct the extraction are, and on the other hand, how many of the annotated text bands are reproducible. The next step for our project is to further develop the GESIS pipeline, which is relate the detected entities with each other, disambiguate the entity mentions, and link the entities, and to apply the pipeline on larger corpora for linguistics like the ACL ontology and a huger subset of archive, namely in the category of machine learning. And additionally, test the domain adaptability on publications from different research domains like social sciences. With this, we could build the GSUB knowledge graph, which integrate all the results and are ready to query, and also, for example, are able to support generative LLMs with traceable information, which is really useful from the research perspective. And finally, we can integrate the results into GESIS services in the GESIS knowledge graph infrastructure, and, for example, with enriching method descriptions and tutorials for the currently under development project service GESIS Method Hub, which showcasing computational methods and tutorials for social science researchers. Lastly, I want to talk about how to use scholarly information extraction systems in production. And I concentrate on 3 aspects which need to be represented in the modeling of such an integration. The first one is usability and extensibility. If you are not able to get additional to get an additional possibility for the user to access and use this information, it's worthless to integrate it. So a user-friendly interface, or from computer science perspective, an API or a knowledge graph query language, which is easy to learn, could help to make the extracted information accessible. And on the other hand, you need a modular architecture to integrate different scholarly information extraction systems in one pipeline. Of course, you need to use scalable approaches to apply your extraction methods on larger corpora and integrate error handling and recovery methods to use in productive systems. And lastly, the perspective of data and system integration. Not only that you need to integrate different extraction results and existing knowledge resources, you also need to be compatible with existing systems in the whole infrastructure. And I want to close this presentation with this short view of how this looks in our system. If you look at the GESIS search and find a publication, you are not only able to find links to relevant, to used research data resources, but you are also able to look at the reference section and follow the link to the full text publication. So finally, scholarly information extraction is able to extract metadata and content information from scientific documents. The approaches can be scaled to large sets of publications. Scholarly IE can help to implement the FAIR principles on research artifacts. Results can be used for new services and support researchers. And if you are interested in conducting scholarly information extraction, requests are welcome. Thank you.